Yeah, and when you fill your car with gasoline or heat your home with natural gas, you're tapping into ancient sunlight. This energy, captured millions upon millions of years ago, comes from a truly remarkable source. It is not from giant dinosaurs, as many cartoons might suggest. Instead, the story of oil and gas begins with the smallest of life forms. These tiny organisms, mostly plants and animals living in the ancient seas, are the true parents of these fuels. Their lives and deaths set in motion a colossal geological process. We are, in essence, using the remnants of their long-lost world to power our own, a connection across unfathomable stretches of time. Imagine Earth, hundreds of millions of years in the past. The continents were not where they are today. The climate was vastly different. Vast oceans covered much of the planet, teeming with life. Among this life were countless microscopic organisms called plankton. Phytoplankton, like tiny plants, captured sunlight through photosynthesis. Zooplankton, tiny animals, fed on the phytoplankton. These organisms formed the base of the marine food web. They lived, they reproduced, and eventually they died. Their sheer numbers, though individually small, were immense. This is where the incredible journey of oil and gas truly begins, in these ancient sun-drenched waters. The sun is the ultimate source of almost all energy on Earth. Plants on land and phytoplankton in the sea are masters at converting sunlight into chemical energy. This process, photosynthesis, is the foundation of life as we know it. When these ancient plankton captured solar energy, they stored it within their tiny bodies. When they died, this stored energy did not simply vanish. Instead, it embarked on a journey downwards. The deceased organisms, carrying their precious cargo of solar energy, slowly sank through the water column. They settled on the floors of ancient oceans, lakes, and quiet seas, beginning to accumulate. This accumulation was not a quick event. It happened over eons, a slow rain of organic matter onto the dark, silent seabed. Think of it as a cosmic dust settling. But instead of dust, it was the remains of life. This process required specific conditions. The waters needed to be relatively calm, allowing the tiny particles to settle undisturbed. Crucially, the environment at the bottom needed to be low in oxygen. This lack of oxygen prevented the complete decay of the organic matter by bacteria. So instead of decomposing fully, the carbon-rich remains were preserved, forming a dark, organic ooze, waiting for the next stage of its transformation. The ancient oceans were alive with an astonishing diversity of microscopic life. Phytoplankton, the tiny plants of the sea, were particularly abundant. They floated in the sunlit upper layers of the water, diligently converting sunlight, water, and carbon dioxide into organic compounds. Alongside them lived zooplankton, the microscopic animals that grazed upon the phytoplankton. Together, these organisms formed a vibrant, invisible meadow in the sea. Their life cycles were short, often just days or weeks, but their collective impact over vast geological timescales was monumental. They were tiny solar batteries, constantly charging and then sinking. When these myriad planktonic organisms completed their brief lives, their journey continued. Their minuscule remains began a slow descent towards the ocean floor. Imagine a continuous, gentle snowfall, but instead of ice crystals, it's a rain of organic particles. This material, rich in carbon and hydrogen, the fundamental building blocks of hydrocarbons, settled in ocean basins, quiet seas, and large ancient lakes. The conditions on the seabed were critical. If there was too much oxygen, bacteria would decompose the organic matter completely, returning the carbon to the water as carbon dioxide. But in many areas, the deep waters were anoxic, meaning they lacked oxygen. This lack of oxygen, or anoxia, was the key to preserving these organic remnants. In an anoxic environment, the usual decay processes are significantly slowed down or halted altogether. The bacteria that thrive in oxygen-rich environments cannot survive, so as the organic matter settled, it was not entirely broken down. Instead, it mixed with fine-grained mud and silt on the ocean floor. This created a dark, organic-rich sediment, a sort of primordial soup for future oil and gas. This layer of ooze gradually thickened over thousands and millions of years, a slow but persistent accumulation of concentrated ancient life. Consider the scale of this operation: tiny organisms dying and sinking, building up layers centimeter by centimeter over unimaginable stretches of time. It's a testament to the power of cumulative small effects. The ocean floor in these specific regions became a repository, a savings account for solar energy captured eons ago. This accumulating organic material was the raw ingredient, the promise of future energy. But it was still a long way from becoming the oil and gas we use today. The next part of its journey involved burial, a descent into the Earth's crust where other powerful forces would come into play. As the organic-rich ooze lay on the ancient seabeds, another relentless geological process was underway. Rivers, flowing from the continents, carried vast quantities of eroded material, sand, silt and clay, out to sea. These inorganic particles, known as sediment, also settled to the ocean floor. They rained down continuously, blanketing the layers of accumulated organic matter. Imagine a slow, steady burial with layer upon layer of this sediment piling up. This process happened over millions of years, gradually isolating the organic deposits from the waters above. The once surface ooze was now becoming part of the Earth's subsurface. The accumulation of sediment was not a gentle dusting. Over geological time, these layers could become incredibly thick, sometimes reaching thousands of meters. Think of the immense weight of a column of rock several kilometers high. This colossal weight exerted tremendous pressure on the layers below, including the buried organic matter. As the pressure increased, the water trapped within the sediments and the organic ooze was squeezed out. The sediments themselves became more compact, slowly transforming into sedimentary rocks like shale, sandstone and limestone. The organic material found itself trapped within these forming rocks. This burial and compaction were crucial steps in the transformation process. The increasing pressure was one of two key ingredients needed to cook the organic matter. The deeper the burial, the greater the pressure. This intense squeezing began to alter the physical and chemical nature of the organic material. It was being condensed, concentrated, and prepared for a more profound chemical change. Furthermore, being buried deep within the earth meant that the organic matter was completely cut off from oxygen, ensuring its preservation and preventing its oxidation back into carbon dioxide. The stage was being set for a slow, powerful transformation. The journey from the sunlit surface of the ocean to deep within the Earth's crust is a long one, spanning millions, even tens of millions of years. The organic material, once teeming with life, was now entombed. It was caught in a geological press, subjected to forces and conditions vastly different from its origins. This deep burial provided the necessary isolation and the increasing pressure, but pressure alone was not enough. Another critical factor was needed to complete the transformation from simple organic remains into the complex molecules of oil and natural gas heat rising from the Earth's interior. As the organic-rich sediments were buried deeper and deeper, they encountered another fundamental force of nature, the Earth's internal heat. The planet's core is incredibly hot, and this heat gradually radiates outwards. The deeper you go into the Earth's crust, the hotter it gets. This is known as the geothermal gradient. The buried organic material, now encased in sedimentary rock, found itself in this slowly warming environment. It was like being placed in a giant, slow-cooking geological oven. This combination of intense pressure from the overlying rocks and rising temperatures from below was the catalyst for profound chemical changes. The organic matter first transforms into a waxy substance called kerogen. Think of kerogen as the intermediate stage, the raw material that will eventually yield oil and gas. As temperatures continue to rise with deeper burial, the kerogen molecules begin to break down. This process is known as thermal cracking. If the temperatures reach a certain range, typically between 65 and 150 degrees Celsius, 150 to 300 degrees Fahrenheit, the kerogen breaks down to form crude oil. This temperature range is often called the oil window. If the burial is even deeper and temperatures exceed this range, the oil itself can break down further, forming natural gas. This is the gas window. Once formed, oil and natural gas are less dense than the water trapped in the surrounding rocks. This buoyancy causes them to migrate upwards. They seep slowly through the tiny pores and fractures in the overlying rock layers, always seeking a path of least resistance. This migration could continue all the way to the surface, where the oil and gas might escape into the atmosphere or form natural seeps. However, for these resources to accumulate in economically viable quantities, they need to be trapped. Geological structures such as folds in the rock layers, anticlines, or faults that seal off pathways can act as traps, preventing further upward movement. These traps, formed by the Earth's dynamic geological processes like plate tectonics, create reservoirs where oil and gas can accumulate over millions of years. Impermeable cap rocks like dense shale sit above these reservoirs, acting as a seal. It is these concentrated deposits that humans seek out and drill for. So the journey from ancient plankton to the fuel in your tank is a story of solar energy, life, death, burial, immense pressure, geothermal heat, and finally, fortuitous geological trapping. Understanding this deep history reminds us that these resources are finite, the product of an incredibly long and complex natural process.